Funding for this program is provided by Annenberg CPB to advance excellent teaching.
As a young physicist in 1905, Albert Einstein gave the world something special, the theory of relativity. A half-century later, in 1955, the year of Einstein's death, the United States is rapidly turning its attention away from a war and the devastating effects of the atomic bomb, and toward a future bright with the promise of a peaceful atom.
Cheers for the creature.
How is it?
Is it scary? My grandmother fainted.
Einstein's ideas have progressed from theory to reality. And in 1955, popular imagination is soaring to science fiction and worlds beyond.
My dad's old card.
And as the creature from the Black Lagoon lurks in the celluloid depths, a young physicist-to-be makes his way to the local theater where destiny awaits. He is about to encounter Einstein's great ideas for the first time.
There's a chill in the air, folks, and that means it's time for the Fall Classic once again, as World Series fever spreads across America. 1955 may prove to be the year of the bums, and that's nothing to cheer about in the Bronx. So let's pick up the action at Yankee Stadium.
Bill Skowron bounces to Padres, and Johnny finally makes the throw to first after the ball stuck in his glove. Bob Cerv sends an easy fly to Amherst, and the Dodgers are only 1 out away from their first World Series title. Padres looks like the coolest person in the stadium. Elston Howard sends a grounder to Pee Wee Reese, and these Dodgers at last are world champions. Delirious with joy, teammates and fans mob the Brooklyn pitcher in wild acclaim. In the Dodger clubhouse is the pandemonium only a great victory can generate. And setting the zany pace are Gil Hodges, Duke Snyder, and Don Newcomb. This is Brooklyn's greatest baseball day. Newspapers shriek the tidings. The Brooklyn Bridge goes topsy-turvy at this monumental event.
Meanwhile, on the other side of the tracks, amateur athletes are already working toward victory in next year's Olympic Games in Melbourne. Australia's down under, but these Olympic hopefuls are already up for the Games.
But the Melbourne Olympic Trials weren't the only games being played in 1955. Just down the street from the Lido, at the legendary Chalkies Billiard Academy, There are things going on in the shadows that even the creature from the Black Lagoon shouldn't know about. At the moment, Bertrand the Machine Gun Berkowitz is fighting to retain his crown. And both the high and low rollers are going for broke. Not surprisingly, the champ resorts to every trick at his skilled and highly polished fingertips. However, under the watchful eyes of the referees, not even the machine gun can break the rules. At least it appears on the surface that some rules simply cannot be broken. They're Isaac Newton's laws of classical mechanics. And at least until Albert Einstein came on the scene, they'd been firmly in place for the past 300 years. According to Newton's first law, a ball won't come to rest unless something stops it. His second law, which remains equally unbreakable, explains how a ball can be stopped, and at the same time, how a ball can be started. The momentum of a billiard ball, or anything else, is equal to mass times velocity. And the momentum is changed only if a force is impressed upon the ball. But when two balls collide, the force on one ball is equal and opposite to the force on the other. And so, the changes in momentum are also equal and opposite. That's why the total momentum of both balls remains constant. And although Machine Gun Berkowitz might not know or care, momentum would continue to remain constant, even in Einstein's theory of relativity.
Bill Haley and the Comets have climbed to the top of the charts with their new hit single, Rock Around the Clock. And in the world of film, there's sad news. Millions of adoring fans refuse to accept the fact that James Dean is gone. But on September 30th, the rising star of 1955 fell in flames. And as moviegoers mourn the loss of the rebel without a cause, the world over has reason to bid farewell to everyone's favorite professor. With Albert Einstein's death, said his friend and colleague I. Rabi, a great light has gone out in the world of physics. Many knew him for the warmth of his friendly personality, his kindness, and his rich sense of humor. Though Einstein's gone, the power of his ideas, which changed the very meaning of time and space, will surely play a role far into the future.
And the game of space billiards, played in the far future, can illustrate one of its more powerful consequences. Albert, like his old friend Henry, gets around at nearly the speed of light. And like the boys shooting pool on Earth, Albert and Henry play their games strictly by the rules. For example, especially in outer space, it's easy to see that nothing is really ever at rest. The difference between moving and standing still depends only on who's doing the looking. But no matter who's looking, Albert and Henry head toward each other at nearly the speed of light. And at the critical instant, Albert tosses his ball upward to coast off into space. Henry likewise launches his identical ball at exactly the same speed. If they both play the game just right, the balls collide in space, and each returns to its owner. To make that happen, Albert sent his ball up with velocity u sub a. And at the same instant, Henry sent his down with a velocity u sub h. With perfect timing, they were on a collision course that sent each one right back where it came from. Each one had changed its velocity by an equal amount in the opposite direction. So, with identical masses, the changes in momentum were as equal and opposite as they would have been back at Chalky's billiard parlor. At least that's how it looked from one point of view. But all serious critics of the game know that it takes a space-time diagram to see things in proper perspective. The spectators may have seen these events this way. But from Albert's point of view, it's a whole new ballgame. With Henry firing first. Then Albert's ball bounces back to Albert, long before Henry's gets to him. In other words, from Albert's point of view, Speedy Henry first got the game going, while Albert waited at rest for the crucial instant to launch his billiard ball into space. The game takes exquisite timing because from Albert's point of view, Henry's billiard ball takes longer than his own to get down to the collision and back up to the ship. If the same thing could happen to two balls colliding on a pool table, it would seem as if the blue ball were more massive because it doesn't get deflected as much as the tan ball. Can that be true, quantitatively? In Albert's frame, Henry's ball was launched at velocity u prime sub h, while his own drifted straight upward at u prime sub a. In the collision, each one changed its velocity, but at least from Albert's point of view, not by the same amount. So, in order to have the same change in momentum, Henry's speedy ball acts as if it has a larger mass. But what is mass? And how can it change with speed?
Record numbers throng into the Coliseum for the 42nd National Automobile Show. It's being held in New York for the first time in 16 years. And as if to make up for lost years, the show is staged on a lavish scale. Power aplenty is represented here. Mighty new engines and power accessories galore on the 124 makes and models displayed. The cars are longer and lower than ever this year, too, thanks in part to the smaller 14-inch wheels. Most of the 51 million passenger cars in use today seem drab and boxy, stacked up against these newest dreamboats. High in the dreamboat class, this one has everything for the busy executive. Makes work worthwhile. There's a trend to the sporty and more colorful. Detroit's designing geniuses keep pace with the nation.
The American automobile may be massive, but even a weightless spacecraft has a certain mass. According to Newton's law, mass is what relates force to acceleration. So, to start with, mass is a measure of how hard a body resists a change in velocity. For example, a car puts up more resistance than a billiard ball. And a ball at rest resists a change in velocity less than a ball in motion. Particularly when it's traveling at nearly the speed of light.
According to the theory of relativity, the mass of any moving object depends on how fast it's moving. The mass, m, is equal to rest mass, m sub 0, times the factor gamma.
So, throughout the universe, mass, like time and distance, depends on one's point of view. In other words, an object's mass depends on its speed.
There's a new television show for the little ones on the Columbia Broadcasting System this fall. It's called Captain Kangaroo. And this week, kids of all ages are speeding en masse to Walt Disney's newest attraction in Southern California.
To all who come to this happy place, welcome. Disneyland is your land. Here age relives fond memories of the past. And here youth may savor the challenge and promise of the future. Disneyland is dedicated to the ideals, the dreams, and the hard facts that have created America, with the hope that it will be a source of joy and inspiration to all the world. Thank you.
Disney had to mortgage his home and life insurance, but it looks like the gamble will pay off in the future. Already at hand on the scientific front, the future is now. In Berkeley, California, Ernest O. Lawrence is already turning Einstein's theories into reality. And the Bevatron, when finally completed, should be able to propel modern physics well into the 1960s. Inside the machine, powerful electromagnetic fields will accelerate tiny particles faster and faster, and finally, they'll smash into other atoms. From the flying pieces,
But wait.
scientists hope to
Since such machines push the particles faster and faster, will they ever reach the speed of light? No, and here's why. Inside any accelerator, electromagnetic fields exert force on a tiny ion. This force increases the ion's momentum, m times v. So the speed increases. But as an object's speed increases, its mass also increases. As it becomes more massive, it becomes harder and harder to make it go faster. The ion's momentum and its energy keep increasing, but its speed never reaches the speed of light, no matter how hard it's pushed. Pushing a body increases its momentum, not only by increasing its velocity, but also by increasing its mass. But what about a body's energy? Anytime a force does work on a body, or a body does work on an object, kinetic energy is increased. And increasing the kinetic energy of an object also increases its mass.
The work done on a body is equal to the force integrated over the distance through which it moves. That work turns into the body's kinetic energy. But force changes momentum. And momentum depends on mass, which also changes with speed. So kinetic energy may be expressed as an integral over changing speed from rest until the force stops pushing. The result looks more complicated than it really is. At low speed, K is 1/2 the mass times the velocity squared. But at higher speed, the curve for increasing energy starts to look just like the curve for increasing mass. The equation shows why. At any speed, the kinetic energy is equal to the change in mass times c squared. And since m sub 0 is the mass of the body at rest, the quantity m sub 0 c squared is called the rest mass energy. Adding the kinetic energy to the rest mass energy gives the total energy of the body.
And there it is, E equals mc squared. In the theory of relativity, energy and mass are one and the same thing. But if added energy adds mass, does an object yield some of its mass if it loses energy? Einstein said it does, and it does, for example, inside the sun. Nuclear reactions reduce the sun's mass by billions of kilograms every minute as it radiates energy into space.
From the first moment man unleashed the power of the sun on Earth, mankind itself has lived under a cloud of potential devastation. But today, scientists are learning to tame the mighty atom and to channel its power toward peaceful ends. At the United Nations Assembly last week, President Eisenhower rose to the new challenge of atoms for peace.
Against the dark background of the atomic bomb, the United States does not wish merely to present strength, but also the desire and the hope for peace.
And in such capable hands, nuclear energy can work toward peaceful and almost limitless possibilities. Those possibilities start to take shape when a uranium atom with a certain rest mass breaks up into fragments with a lower total rest mass. That small difference in mass equals an enormous amount of energy. And that energy can show up in a variety of uses. Last month, Arco, Idaho became the first city in the world to be lit by atomic power. Where, when, and how it will end is still a matter of speculation and a concern of the scientists of tomorrow.
But no matter where it ends, it all began with Albert Einstein. Playing by the rules, Einstein discovered that mass changes with speed. And that mass itself must therefore be one and the same with energy.
Obviously, in 1955, the atomic age has arrived.
Funding for this program is provided by Annenberg CPB to advance excellent teaching. For information about this and other Annenberg CPB programs, call 1-800-LEARNER and visit us at www.learner.org.